Hello guys, and welcome in this new episode. Today we will continue with the pre-computed atmospheric scattering. Last time we just provided an overview of the implementation that I started to work on in WebGPU, and this is basically where we stop, just providing an overview of the initial atmosphere model and the initial unit test that I provided, which is doing all the pre-computation on the GPU and then providing the final texture. Today, what we will do will be to try to create an additional unit test to focus on the computation of the transmittance texture itself, and we're going to replicate the computation that is done on the GPU but on the CPU side, so with C++ code, and try to compare the results that we get on both sides to see if there's a match. There should be a match actually. If there's something not matching, it means that either the GPU algorithm is faulty or the CPU test code itself is faulty. So we will work on that until we get test passing on this texture. So first thing we need to do is to add a new unit test for that. I'm just duplicating the previous unit test here, and I'm changing the name of the second test to test transmittance computation instead of test create atmosphere model. Now we're just going to compile this and try to execute only this test, I guess. And so to run this test, all I need to type is this specific filter. We are in this test suite, and now we need to execute this specific test. And obviously for now it's just doing the same thing as in the previous test, so nothing changed here. After that, the first thing we need to deal with is to try to retrieve the actual texture content that we have on the GPU but on the CPU side when we're done with the computation on the model side. If we look at the atmosphere model, we see that inside the class we have this transmittance texture. This is where the final transmittance result will be stored. So we need to kind of provide access to that somehow. Let's just add a function to provide access to the texture. Here is the function I just created to retrieve the transmittance texture from the atmosphere model. Next, in our unit test, we're going to retrieve that transmittance texture once the pre-computation is done. And we need a mechanism to actually read the content that is inside that texture into a buffer. And then we're going to read the content of this buffer on the CPU side. For that, I'm going to refer to some of the unit tests I created on the texture themselves. So for instance here, I have a unit test where I am creating a texture, and then I'm trying to write some data in that texture, and eventually I'm going to create a buffer with the appropriate size, and we're going to copy the texture into the buffer itself, and then we're going to wait for this to finish and map the buffer to read the data back. So we're going to get mapped data here and read that, and eventually we do a comparison, and this should be where we do the actual check of the data ourselves. So let's try to replicate this code. Once we have the transmittance texture, I have been thinking a little bit about that, and I think we could try to do something like this. I can maybe provide a function, which is this one, the read texture data, which will take the texture itself and a vector of unsighted char elements, and it should try to read the data from the texture and fill this vector with the appropriate data. Once this is done, well, the function I guess could return true on success or false if there's something going wrong, but I'm not sure you could actually get something going wrong without producing an exception, we can maybe change that. But anyway, after that, first thing we can try is retrieve the actual texture width and height and compute the total byte size of the texture, which would be width multiplied by height multiplied by 4, because the transmittance texture is actually an RGBA plot32 format texture. So it means that for each pixel we have 4 channels, and each channel is taking 4 bytes. Once we have the complete size of the texture, we should compare that with the size that we have in the data, which should be the same size. Next, we need to focus on the implementation of this read texture data function. I am thus declaring the function in the WebGPU engine itself. And actually, thinking about it, I think I should rename this function to debug read texture data, because I really don't want to use this function at runtime or anything, because it's going to be very inefficient, and I mentioned that also in the documentation here for that function. Actually, here we're going to make a copy of the texture in a buffer, and we're also going to copy the content of the buffer into a vector of inside a char afterwards. So a double copy operation, I guess. Not very good, you don't want to do that at runtime. And for the implementation itself, here is the beginning of what I am currently writing. First thing we need to do is to retrieve the size of the source texture and also the format of that texture to be able to figure out the number of channels that we have for this format and what is the actual size and number of bytes for each channel. Then with this we can compute the number of bytes that we have on each row of the buffer where we want to read the actual content for the texture. So to compute this, we need the width of the texture, the number of channels, and the channel size, and we need to take into consideration that the buffer itself should be aligned at 256 bytes, so the number of bytes per row could be a bit larger than the actual number of bytes that we have per row in the texture itself. And using this, we're going to use the number of bytes multiplied by the texture height value in this case, and that's what we use to create the actual buffer. Then we're going to start building some commands, and we're going to request a copy of the texture, which is the source in this case, into the buffer that was just created. And we will just submit those commands afterwards, and we're going to wait for the engine to be idle. I'm wondering if this step is really necessary. Maybe not, but I'm not quite sure, so let's just leave this here for now and think about it maybe. Alright, so thinking about it a bit more, I don't think that this first wait idle call here is necessary, because after that we're just going to request the async mapping of the buffer, and we're going to wait again to ensure that this operation is done. And I'm pretty sure this will force all the previous operation to be completed also. So I think we could try to just remove this call and see if it's working fine, and maybe we need to experiment a little bit about this point. Next thing we need to do is, well, I don't think we need that, is to retrieve an actual pointer on the mapped data starting from the very beginning of the buffer. So this is going to be our ptr variable here. It should really be not null pointer at this point. And next we can start with resizing the data vector where we want to store what we're going to read. So to resize that, we need to use the full size of the texture. And now I'm also realizing that I'm going to need this, and I'm going to need it again here when I do the copy operation. So maybe I could just give this a name, and I could just maybe say size t stride is this value. Alright, once we have this stride value here, which is multiplying the height value by the stride here again, and next for well, here we're just going to do a copy operation, so we can just do mem copy actually. Destination would be what we have as a current destination pointer, because this is what we took here for the data. The source is going to be what we have for the current source pointer, and here we're not going to convert that to half. Wait, what is that? No, that's still just PTR, and that's going to be plus equal this offset. Number of byte by per row is taking into consideration the alignment value here. Alright, so you may want to offset the pointer. Actually, you basically don't have to do it here, you can do it afterwards, just adding byte per row value. And for the destination, you're going to just add the stride value, and to do the copy, you're just going to copy stride elements, and this part here is not needed anymore. Alright, and after that you can just unmap your buffer because you're done with the copy operation. Alright, and that's it. This function should be able now to copy all the data we want into the data vector, and we can just try to check if this one is working fine, but it doesn't seem to be the case here. Oh yes, the function we use now is debug. Let's rebuild. Actually, yes, this function should also return something, so it should return true when we're done. In fact, this result is probably not needed because it can only return true. But never mind, we're just keeping this for the moment. I'm also now just reporting the total size of the texture here in the unit test to see something different at the end and ensure that I'm actually running something different. Okay, so first execution of this unit test didn't work because as you can see here, there's a validation error because the transmittance texture contains texture binding and storage binding usage, but it doesn't contain the copy source flag, and we actually need that because we're going to do the copy texture to buffer operation. Problem here is that generally speaking, I don't really want my transmittance texture to have this copy source usage because this mean that maybe the texture storage on the GPU could be suboptimal, so we should avoid that. And to avoid that, we need to have a staging texture, and we need to copy our actual transmittance texture into the staging texture, which should have this copy source flag, but that means another processing pass to do a copy operation. But otherwise, another option that we have here is to add another parameter in the threads that we use to construct the atmosphere model. So with this additional parameter, we could specify whether we want to use the copy source flag or not when allocating the texture. And next, when we are actually creating the texture object here, as you can see, we are preparing a usage variable, and we use that for the texture that are stored in the class. Yes, all of them are using this flag. So what we could do here is we try to check with the threads. If the threads have this value set to true, then we also add that to the usage, the texture usage copy source flag, which means that now we need to also specify the value true for this thread element when we prepare here. We're creating the threads, So we could just add here thread sum and 2 for this value. Alright, with this simple change, the unit test is now working properly and it's returning the size here of the texture. Let's just check if the size here is correct. And indeed, if you multiply the texture width and height and the number of channels and the channel size, this is a value that we will get. So everything seemed to be in order. Now we could try to do a first test and try to display some of those values. They should not all be just 0 or something like that, for instance. Alright, and so just trying to retrieve a pointer on the data that we read from the texture and converting that into float values, we see that if we try to display a few of the first initial values in the array, we get non-zero values, which is great. And we see that every time we get 3 non-zero value, then a 0, which is expected also because we all actually have an RGBA texture, but we are only writing data into the RGB channels. And if we check the pre-compute transmittance shader, we see that when we are storing the computed value, we have this transmittance vector, which is a vec3, and we set the value 0 in the alpha channel. Say we would write something different like here, like 42 for instance, and we can rerun the unit test with this change. And now we get exactly what was expected. The alpha channel will report the value 42, which is great and consistent with what we're writing here. So yes, this is alright already, but this recording took me much longer than I was expecting, so I'm going to stop here for the moment and we're going to continue this unit test writing in the next recording. So thanks for watching and see you next time. Bye bye.